3 trusses. A truss is a structure made up of slender members pin-connected at ends and is capable of taking loads at joints. They are used as roof trusses to support sloping roofs and as bridge trusses to support deck. In many machines, steel trusses are used. Transmission towers are also the examples of trusses. In the case of wooden trusses, the ends are connected by making suitable joints or by nailing and bolting, whereas in steel trusses ends are connected by bolting or welding. The trusses are also known as pin-jointed frames. A truss in which all the members lie in a single plane is called as a plane truss. In such trusses, loads act in the plane of the truss only. Roof trusses and bridge trusses can be considered as plane trusses. If all the members of a truss do not lie in a single plane, then it is called a space truss. Tripod and transmission towers are the examples of space trusses. In this chapter, the analysis of only plane trusses is considered. 3.1 Perfect, deficient, and redundant trusses. A pin-jointed truss which has got just sufficient number of members to resist the loads without undergoing appreciable deformation in shape is called a perfect truss. Triangular truss is the simplest perfect truss, and it has 3 joints and 3 members, Fig 3.1. Perfect trusses with 4 and 5 joints are shown in Figs 3.2 and 3.3 respectively. 2 trusses shown in Fig 3.4, A and B, have the same number of members and joints. The truss shown in Fig 3.4, A, is perfect, whereas the one shown in Fig 3.4, B, is not capable of. It may be observed that to increase one joint in a perfect truss, 2 more members are required. Hence the following expression may be written down as the relationship between number of joints J, and the number of 3 Fig 3.1 members M, in a perfect truss. M equals 2J3, 3.1, 244. However, the above equation gives only a necessary, but not a sufficient condition of a perfect truss. For example, the retaining its shape if loaded at the joint mark 6. Therefore, the only necessary and sufficient condition of a perfect truss is that it should retain its shape when load is applied at any joint in any direction. 12132 Fig 3.213315565 35634247115 Fig 3.33, B, 3, A, 5246246P151 Fig 3.4 A truss is said to be deficient if the number of members in it are less than that required for a perfect truss. Such trusses cannot retain their shape when loaded. A deficient truss is shown in Fig 3.5. A truss is said to be redundant if the number of members in it are more than that required in a perfect truss. Such trusses cannot be analyzed by making use of the equations of equilibrium alone. Thus, a redundant truss is statically indeterminate. Each extra member adds 1 degree of indeterminacy. For the analysis of such members, the consistency of deformations is to be considered. The truss shown in the Fig 3.6 is a typical redundant truss. In this truss, 1 diagonal member in each panel is extra. Hence it is a 2-degree redundant truss. In this chapter, only the analysis of perfect frames is considered. Fig 3.5 Fig 3.6 3.2 Assumptions in the theory that is going to be developed in this chapter. The following assumptions are made. 1. The ends of the members are pin-connected, hinged. 2. The loads act only at the joints. 3. Self-weights of the members are negligible. 4. Cross-section of the members is uniform. If at all the cross-section varies, the center of gravity of the section is assumed to be located along the same longitudinal line. In reality, the members are connected by bolting, riveting, or by welding. No special care is taken to ensure perfect pin connections. However, experiments have shown that assuming pin-connected ends is quite satisfactory since the members used are slender. Even if a load is not acting at a joint, it can be replaced by its reaction at the joint and a local bending effect on the member. The frame may be analyzed for the joint loads and the local bending effect on the member superposed in the design of that member. In most of the trusses, the self-weight is really small compared to the loads they carry. Hence self-weight of the members may be neglected. It is the duty of construction engineer to see that the centroid of all cross-sections lie along a single axis so that the member is held in equilibrium by the two forces acting at its ends. Because of the assumption of pin-connected ends, it is more appropriate to call the theory that is going to be developed in this chapter as analysis of pin-connected plane trusses. Analysis of rigid frames is not covered in this book. 3.3 Nature of forces in members. The members of a truss are subjected to either tensile or compressive forces. A typical truss ABCDE loaded at joint is shown in Fig 3.7, A. The member B is subjected to compressive force Ca shown in Fig 3.7, B. Effect of this force on the joint B, ORC, is equal and opposite to the force C as shown in Fig 3.7, Fig 3.7, B. The member AEI is subjected to tensile force T. Its effect on the joints A and ER as shown in Fig 3.7, B. In the analysis of frame we mark the forces on the joints, instead of the forces in the members as shown in Fig 3.7, C. It may be noted that compressive force in a member is represented in a figure by two arrows going away from each other and a tensile force by two arrows coming towards each other. This is quite logical considering the fact that the markings on the members represent the internal reactive forces developed which are opposite in direction to the applied forces. Compressione tensio and Fig 3.7, C. 3.4 Methods of analysis. The following three methods are available for the analysis of pin-connected frames. 1. Method of joints. 2. Method of section. 3. Graphical method. The first two are analytical methods and they are dealt in this chapter. 3.5 Method of joints. At each joint the forces in the members meeting and the loads acting, if any, constitute a system of concurrent forces. Hence, two independent equations of equilibrium can be formed at each joint. First, a joint is selected where there are only two unknown forces. Many times such a joint can be identified only after finding the reaction at the support by considering the equilibrium of the entire frame. Then making use of the two equations of equilibrium at that joint the two unknown forces are found. Then, the next joint is selected for analysis where there are now only two unknown forces. Thus, the analysis proceeds from joints to joint to find the forces in all the members. It may be noted that if there are a j number of joints, 2j number of the equations can be formed. There will be three reactions in a general determinate truss. The force in each member is unknown. Hence, if there are a number of members, the total number of unknowns will be m plus 3. A problem can be analyzed if there are as many equations as there are unknowns. Hence, a frame analysis problem is determinative, 2j equals m plus 3, 3.2, this equation is the same as equation 3.1 which was derived on the consideration of a perfect frame. Hence, a perfect frame is determinate. If M2J3, then the number of unknowns is more than the number of equations. Hence, a redundant frame is indeterminate. If MEL2J3, then the number of equations is more than the number of unknowns. Since a set of solutions can satisfy such equations, it shows instability of the structure. Hence, a deficient frame is not stable. The method of joints is illustrated with the examples 3.1 to 3.7. 40 knots examples. Example 3.1. Find the forces in all the members of the truss shown in Fig 3.8, A. Tabulate the results. 3m EAB theta d theta 3m 3m C Fig 3.8, A.